Hi, this is John Keller. This is a video showing how to log on to WebMO and set up and run a small computational job. We'll use formic acid, whose Lewis formula is shown here as an example. Start at the information page of the UAF Computational Chemistry site, which has directions for logging on and a link to the login page. Click the graphic at the top right corner. Log in with your UAF username and password as you would for Blackboard. The first time you log in, you will also need to choose a group. Your group and the group password will be assigned by your lecture instructor. Clicking the Login button takes you to the Job Manager page in WebMO. First, create a new job. This shows the different tools that you can use, and across the top, some menu items. Start by connecting the formic acid atoms with the Build tool. This automatically starts with carbon, so when you left-click, it puts in a carbon atom. Now use the periodic table to choose oxygen, or hit O on the keyboard. Click and drag a line across which makes a bond. The second oxygen is attached to carbon. And one of these has a double bond. Now add two hydrogens. You usually need not be too careful in drawing a particular geometry. Whether it's drawn accurately or not, WebMO uses a cleanup step to insert standard bond distances and bond angles. This is done so that the optimization process has a good chance of success. Check out some of the other tools in the toolbar. The Rotate tool is vital for providing 3D visual clues that cannot be perceived in the static 2D image on screen. In this case, for example, you have to rotate formic acid to see that it is perfectly flat. With the Zoom tool, left-click and drag up to zoom in. Use the Adjust tool to select different parts of the molecule, such as atoms, bonds, bond angles, and dihedral angles, that is, 1, 2, 3, or 4 atoms in a row. Thus, if we select the OCO bond angle, we see it equals 120 degrees. This is the standard value for a trigonal planar atom, which WebMO installs in the cleanup procedure. On this page, choose the program that will do the actual calculation. We'll use Gaussian, an all-purpose research and teaching program with many built-in quantum methods. Under Servers, WebMO will automatically assign this job to one of several servers that are running in the background. Put in a useful job name here. Gaussian can carry out several different kinds of calculations besides geometry optimization. Method and basis set are explained in the experimental handout. The defaults entered here provide a balance of accuracy and speed. The total charge is 0 for a molecule, and multiplicity equals 1 for all molecules and ions in this experiment. Multiplicity is greater than 1 only if an unpaired electron is present. It is not normally necessary to open the Preview tab, but if we do so now, you can see that WebMO is actually creating a text input file for Gaussian. This includes the method, basis set, calculation type, which here is optimization, charge, multiplicity, and the XYZ coordinates of the atoms. Now submit the job by clicking Continue. After the job has been submitted, check the status column. It will first show queued, and then running. When the job is complete, check the View Job icon or the job name. Now you see the formic acid molecule as it is optimized with density functional theory. This is very close to the, quote, real geometry, unquote. It is trigonal planar as originally shown in the WebMO cleanup model. However, the bond angles in the optimized structure differ considerably. For example, instead of 120 degrees, the OCO angle is 125.1, and the internal HCO angle is 109.5 degrees. Farther down the page, you see other notable results. The total energy of the molecule is minus 186.76 hartrees, where 1 hartree is 627 kilocalories per mole. This is the energy of the molecule in the gas phase relative to the 29 separate particles, that is, 5 nuclei and 24 electrons. This is a very large negative number, mostly due to the stability of 5 atoms relative to the collection of free particles. In the next section down the page, you see how the energy changes during each step of optimization, where Gaussian has repeatedly adjusted the geometry until the energy is essentially constant. That's how you end up with a stable structure. Okay, now go back to the job manager and log out.